Good morning, Dan.
Chris, is that you?
This is Chris.
How are you?
I am doing well. I saw that it popped in. I got notification that you had joined the meeting. So I figured it was perfect time to troubleshoot and make sure we've got connection for you.
That sounds good. I seem to have lost a screen that I had before with regards to sharing. Although I had it on a second ago. Let me just click on this. Make sure.
I'm Andy Chapman. I'm one of the account executives in Atlanta, Georgia. Obviously, we've got people from all over the Southeast that are here today. So if you guys have any questions that pop up, go ahead and feel free to put them in the chat and we'll try to answer them as they come in. Additionally, feel free to reach out to your specific account executive, whether in North, South Carolina, Georgia, Florida, if you've got specific questions that we couldn't answer on this. We've got Dan Mason with us today from BioClimatic, and he's going to be talking about air purification and pathogen control in HVAC systems. And Dan's been around for a while. He's a wealth of information, and I know he's going to do a good job presenting to you guys today. So without further ado, I'll let Dan chime in.
Yeah, thank you, Andy, very much. Appreciate everybody participating here today. We have a few slides here to go through that hopefully will bring everybody kind of at a level playing field with respect to air purification, and in particular, as we're looking at our new friend, the COVID-19 virus. The company's been involved, and he said, for quite some time with air purification. We deal with VOCs and toxins and odors, all sorts of different contaminants of concern in several different types of markets. And as of about 3 or 4 months ago, we got a pleasant surprise here with much more of our focus now being on pathogen control, whereas we certainly did it from time to time. It was one of many. Now it seems to be dominating the equation. And I guess hence the call for this webinar. So I'll go through several different technologies, kind of talk about some pros and cons, application concerns, in providing some food for thought for HVA systems, for indoor air quality, with the particular focus, obviously, on the COVID-19. That said, some definition here with different names. I'm sure you've seen most of these through the press and conversations. And of course, the obligatory factoids here at the beginning of the presentation, with these numbers unfortunately changing day by day. And an interesting comparison here to the last really major pandemic from 100 years ago, where in fact what we're seeing here is pretty stunning with respect to the rate of the problem as compared to what occurred back in 1918. The obviously effect on the economy, and what we're now seeing is a lot of folks saying, well, it's time to now open up a little bit, but what are we going to do with our offices? What about our classrooms? We need to do something. We need to be somewhat proactive in addressing this new concern within our HVAC systems. So again, let's go into that in some more detail. What are we actually trying to tackle here? A lot of changes in terms of the information that's coming out to us. It's very much dynamic with regards to what the World Health Organization says, or NIH, or the CDC. Things changing on a regular basis. Here back a couple of months ago, the European Heating, Ventilating, and Air Conditioning Association providing some information saying that surface contact was certainly very much a concern, as well as the large droplets. And then more recently, CDC coming out and saying that surfaces really are nowhere near that level of a threat. And in fact, it really is being spread by the air with the respiratory droplets of bioaerosols that are of the primary concern. So we're trying to track all that as time goes by and keep our information up to date. And hopefully what I provide here today is in line with that. Just a quick disclaimer here, because of the things that are changing so often and because we can never say 100% with regards to an effectiveness, just a quick disclaimer here that we're providing our best information, best practices as we know them today. And over time, I'm sure some of that will be revised and updated, but just, of course, the obligatory statement here at the beginning of our program. So I'm going to go through, I think, 4 different types of technologies, starting with particulate filtration. Everybody's familiar with conventional filters used primarily to keep your rooftop equipment clean, keep the coil clean. Secondarily, perhaps indoor air quality, although that's changed over time. A whole pile of different types of products that are out there with the engineering behind that for the pressure drop, the energy costs associated with those pressure drops, the costs and so forth. Very well known. Efficiencies probably in the MERV 6, MERV 8 that's been being used on your conventional typical equipment, with obviously efficiencies for MERV values going up much higher than that. And the upper ones, MERV 15, MERV 16, having a capability of trapping some bacteria and some virus, and obviously for pre-filtration to a HEPA. And then HEPAs, where really you're looking at the gold standard with respect to going after the smaller particles, and that's where you're seeing the sizes of the bacteria and the viruses that, of course, are of concern here today. This is an older chart from ASHRAE. They said you're free to use this with regards to presentation materials. I use the older chart because the top section showing MERV 17 through 20 is no longer on the MERV chart. The new ones, you'll see it stop at the MERV 16. This has some nice information, however, with the older chart that I like to refer to, and in particular particle sizes. The reference to viruses unattached, that would be the ones that are really by themselves, not included within bioaerosols, references to bacteria, and over to the right, specifics with regards to the size of the particle that can be captured, the 0.3 microns, a significant piece of information with regards to how they rate them that way. That comes into play when we're looking at the coronavirus with its particular size. Again, on HEPAs, 99.97, or you can get a little bit of an upgrade to 99.99, really a change in the sealing mechanism to give you a little bit better control of any bypass. Very much used with regards to airborne disease transmission. Of course, clean rooms and the like. If you're looking for really going to the full extent where you may actually have an infectious disease control area that you really cannot take any chance, you might go to the ULPA, which is very good with regards to even smaller sizes, has been used for other types of medical procedures where you really need to have nothing in the air. So that can be considered for the absolute best in terms of the approach. More information on all this being available from the ASHRAE handbook, as you can see here. But with that, we're looking at the COVID-19 being at that smaller size, about 0.1 micron. Most of them, however, that are viable are actually being carried in bioaerosols. This is from your sneeze, your cough when you're speaking, and then in fact are really the concern for what can actually be drawn into the body and create problems. So this is in the range where we're looking at with that HEPA filter. Not to say that the MERV 13, 14, 15, 16 won't contribute, they certainly will. But to the greatest extent, you'd want to shift gears to the HEPA filtration itself. Some of the physical concern for us working with HVAC, the particles that we're going to be looking at are the ones that are the small size, that remain airborne, that where gravity really doesn't have too much of an effect. Larger droplets obviously falling, as you can see by that graphic there. The red dots are the ones that they say we need to keep our 6 feet social distancing. It's the green ones that we're going to go after. And actually, just a quick sidebar, obviously the system that we might provide in terms of a solution for going after the COVID-19 virus, we can only treat what gets drawn into our system. The smaller particles are the ones that are the problem for people, and they're the ones that are airborne and can be returned to our system. So perhaps that's a silver lining with regards to what we can do to address this particular concern. This is an interesting slide here when we're looking at the HEPA filter, the physical capture of the particles of the virus. These are different types of capture mechanisms. HEPAs are different than your MERV 16 and lower filter in that they're not really looking at a sieve approach. It's not that you have a particle too big to squeeze between the fibers. You're looking at different types of that interception of the particle. with the diffusion to the left for the very, very small particles actually getting into things associated with Brownian motion, certainly not a sieve with regards to how it actually functions. But then in the middle of that graph, you'll see the dip, and that corresponds to that 0.3 micron rating of HEPA filters. There is, for some reason, and I can't tell you exactly why, that particular point is where HEPAs seem to be their weakest in terms of capture, and hence they use that to be conservative for their rating point. Again, the COVID virus being about that 0.1, the bioaerosols would be from that maybe 0.1, 0.3, and then over to the right from the graph that you see here. In all cases, let's look at some practical considerations with the filters. They're only as good as what's going through the filter. If you have bypass, if the filters have not been installed properly, obviously you're not going to get the performance you're looking for. On retrofits, you may be somewhat limited in terms of what you have in terms of the frames. In new design, you'll have a little bit more flexibility and liberty to be able to select things that might be a little bit more capable with respect to the framing and the sealing itself, the physical sealing of the filters, which can work to your advantage. Again, on retrofits, certainly recommend if you had a MERV 8, taking it up to at least MERV 13. You can get that in a 2-inch size, which should fit your rack quite readily. As you get to MERV 15 and 16, you're going to go to a deeper filter, and that may present problems for existing systems. And obviously, HEPA is 4-inch to 12-inch. Clearly a velocity-dependent filter in terms of your selection. Some of them are only rated to 250 feet per minute, which is about half the velocity of what you're going to see across a cooling coil. So again, the design is important in terms of how you approach the filtration selection to give you the best performance, but practically being able to be applied to either an existing system or the new design that you're working with. We know that they impart a pressure drop. So if you up your efficiency, that pressure drop's likely to go up. You need to consider that for your blower capacity on the existing system. The numbers here point to, which would be maybe that MERV 13 up to over an inch. When you're adding a HEPA filter, the blower that's got to be capable of handling that, but also that does not include loading. So the pressure drops will be even higher as the filters do load over time, something that certainly needs to be considered, whether it be retrofit or a new design. There's costs associated with these filters, more expensive than just your MERV 8 throwaway. So there's some maintenance costs associated with that. To try to optimize the life, you may want to add filter gauges to say, hey, we don't have to change them any sooner than necessary. That might be a good investment with regards to the economics. And the last note here, I think this is good for any filter, certainly in this day and age, but using the gloves and mask, your PPE, for the service technician, I think there's a very good idea, good practice in general. But as you move toward more critical applications, maybe you have an infectious disease ward of some sort, you may even need to consider a much more substantial system where you have a bag in, bag out, where the technician never comes in contact with the filter itself. Again, that would certainly be application specific. Okay, let's switch to number 2 here, bipolar ionization. I'm going to guess that most of you are somewhat familiar with this technology, this type of product. It's been around for quite some time, quite a bit over the last several years with regards to indoor air quality procedure, reducing outside air, doing some air cleaning for the purpose of being able to save energy by not having the added load of the ventilation air that comes into a system. Today, I'll just talk about it here with respect to our concern on COVID-19. But basically, this is a device that has a pair of electrodes with a high voltage potential between them. And it imparts energy, if you will, into the airstream that causes molecules to basically break down and these hydroxyl radicals to be created in the presence of water vapor. And it becomes a sort of chemistry kit, if you will, where there's lots of changes going on with molecules. These radicals are very strong cleaners of the air, as suggested by this graphic in the upper right. This is a professor in Germany working with air quality, and I think he wanted to impress upon his students that these OH radicals were like Windex in terms of cleaning the air. Certainly very, very effective. Today, of course, the interest is saying, hey, great for using it for reducing outside air perhaps, but can we also apply this for addressing the virus concern? Let's talk about how that works and how it connects for bipolar ionization. This graphic shows from left to right a contaminant. We're going to look at ammonia as an example here. that passes across an ion generator. Again, this energy, if you will, being imparted to the airstream, and the molecules break down into ions. You have the formation of these hydroxyls that get into the mix, and with random collisions of these molecules, and we're talking about millions of them per second, over toward the right size, they recombine, they reassociate into water vapor, oxygen, nitrogen molecules. Everything looks beautiful. The ammonia is gone. That's basically the principle of the operation. But from this graph, you should not take away a conclusion that these particular devices are 100% effective in terms of a single pass. You will not see all of the ammonia removed, as is this particular example. I would estimate, depending upon the conditions and the contaminants, you're probably looking at anything from 10 to maybe 25% single pass reduction of some of these types of contaminants. But our concern is like, hey, okay, contaminants are fine. What about our topic today, the coronavirus? A graphic here that shows exactly how that works, where in fact, those OH radicals are looking for a hydrogen to complete the return to a water vapor molecule, if you will. And the viruses gladly give up from their protein membrane that hydrogen, which basically renders them inactive. So this is a function that happens with bipolar ionization when you're looking at cells, or for that matter, viruses as well, in disrupting that ability to replicate. Very busy slide. I'll take you into really just one part of it here. We've had several tests made over the years showing the effectiveness of the ionization against different types of microbials. Fungus tends to be a little bit more difficult in general. They're the larger, stronger cell, if you will. Viruses being a little bit more susceptible, I guess that's a good thing. And you can see here a couple of influenza studies that have been done where you see a removal rate of 99%. As with a graphic where I suggested you're not going to get 100% on a single pass, these are our chamber tests. So you're looking at a known quantity of virus that's been injected. You turn on the bipolar ionization device in a closed environment with no changes, and you watch what happens over time. This is an ideal. It does not represent HVAC. So once again, when you're looking at is the hydroxyl radical going after a VOC, or is it going after a COVID-19 virus particle? You know, we don't know exactly what that mix will be at any one point in time. What's the humidity? Lots of different parameters that come into play. I would suggest, and this is truly a swag, that on an HVAC system with needlepoint bipolar ionization, that in fact you'll be getting maybe 10% to 15, maybe 20% on a single pass with regards to being able to deactivate the virus. So 99% shows it is very effective. In reality, I think you're almost certainly going to see something less than that, just in terms of the reality check. The device itself, we call this needlepoint because you have these two little needles, little pins. Those are the electrodes with a high voltage potential, with the air gap being the dielectric. And again, how the energy is imparted to the airstream. Very small, very flexible in terms of it being installed in a system. The upper photograph here is showing one of those modules of many on what we call a rail or a bar that might go across a large plenum, across the face of the front of a cooling coil in terms of its width. The lower right would be an assembly we might use for a duct application. So again, there's lots of flexibility. We can populate them as necessary for the airflow for the application to give you the performance that you're looking for. And here's some photographs showing on just single modules in the left and lower center, a sealing unit. You're looking up at the ceiling here. The air filter has been dropped down to the left. You can see that hanging down there to the left. And you can see the one little module with a bright blue LED shining at around 10 o'clock on that circular return of the sealing unit. Very small, very compact, can be easily installed in these types of systems. Also for small systems like fan coils, or larger systems with the rails, as you see on the right with a rooftop unit. Most of the air filters have been removed. You can see the one in the back, and then you can see the rail running along the top. It looks like it's got 1, 2, 3, 4, about a half a dozen of the modules that you can see across the top of that cooling coil. Some considerations for ionization. We would like to see them downstream of a pre-cooling coil. These have a little static charge that may be associated with it. Any dirt that gets on the needles over time will reduce its ability to put off the ionization that you're looking for. We do suggest that they are installed perpendicular to the airflow perpendicular to the needles, not like what we see over here to the right, which was a photograph of something that was installed improperly where the air is hitting it face on. That should be rotated basically 90 degrees to allow the air to go across the face. Not a huge consideration, but certainly best practice. And we do suggest that they be turned off when the fans are turned off. This does help extend the needles with regards to long-term resiliency, longevity. Not necessary again, but best practice. You need to have the inspection capability. They do need to be cleaned periodically. Obviously, the better the pre-filler, the less often that would be required. And you do need a note that I add here, because we've learned maybe the hard way that these require about 3 inches in the direction of airflow. If I back up here a minute, you'll see the rooftop unit over here. This is a unit that actually had about 5 inches between the back of the filter and the beginning of the cooling coil. It was wonderful, but we've seen some where you can hardly get your fingers between the filter and the coil. And you want to keep that in mind, certainly, as you look to install these. We'll work with you in that case in terms of perhaps a better location to make sure it can be installed and be effective as well. Making sure that they're actually doing their job. It's not like a light bulb where you flip a switch and you can see something. The LEDs really are going to give you that 99% assurance. Just like an electromagnet, you put some power to it, you're going to get magnetism. These are just simple passive devices. When you put power to them, you're going to create that high voltage potential, and you're in good shape. For those that say, hey, I need to do some documentation on this, you can go forward with a handheld device to actually see if there's ions being produced. We could provide a sensor on the lower left that actually can be installed that will give you a feedback on a BMS system saying, hey, we see that you've turned the modules on, and yes, we do see ions, and give you that confirmation if in fact that would be appropriate. You can see a fellow here on the far lower right with a sensor up by the ionizer checking for the operation. Number 3, ultraviolet irradiation, germicidal UV, UVGI, the C-band of ultraviolet, very well known for its ability to deactivate pathogens, microbials, and it basically does this by getting into the contaminant of concern here and basically preventing it from replicating. It breaks up, you remember from your chemistry days, the 4 different types of acids that are required for DNA and RNA replication. It interrupts that particular process. That's about as much as I can tell you on that. You're going to take me beyond my level of expertise, but has been very effective, been ubiquitous in use in some areas for quite some time. Lots of flexibility in terms of how it can be installed for air handlers or for inducts, standalone systems. Although you do have to do some engineering to make sure you're going to apply the ultraviolet light appropriately. The UV itself, why do we use that particular UVC lamp? It's because, in fact, the microbials you see in the right-hand graph basically have their weakest point around 265 nanometers. They succumb most easily at that particular wavelength. And in fact, the lamps are very, very close to that, emitting about 254. So very, very effective in terms of killing off these pathogens that we're concerned with. Lots of parameters that we look at. We're getting several calls for UV in terms of how they can retrofit or introduce the UV as a solution. And we look at several different things to make sure we select the lamps appropriately. Intensity, there are standard output, there are high output. Do we have them in terms of more lamps or fewer lamps? What's the reflectivity of the enclosure? So the light's going to do more for us than a single shot off the bulb, but actually reflecting back in to continue to do its job. It turns out that slightly warmer air is better than slightly cooler air. We can size it for the air coming off of the cooling coil. That's not a problem, but it's certainly good to know that. There's probably a 15–20% difference in terms of effectiveness by having the warmer air. So if you can put it in the return air stream instead, that's to your advantage. Duration, obviously, the longer the pathogen is exposed to the light, the less likely it's going to survive. So lower velocity, better than higher. Duct runs, we have to be very careful with that because you can see some duct velocities that are easily over 1,000 feet per minute, and that's not best with regards to applying UV unless you've got a very long straight run where we can really populate that straight run with lamps to make sure it overcomes the high velocity. And last, the type of pathogen. Viruses and bacteria are much weaker with regards to its ability to resist UV as compared to the fungus, the mold spores. And again, that in this particular case works to our advantage. Some applications have been used quite a bit in the past, what we call coil maintenance, where we have a standard output lamp and not necessarily a whole lot of them, for the purpose of getting rid of mold or preventing mold formation on a damp, cold side of a cooling coil, the drain pans, to prevent a buildup of the mold in the fins that creates a pressure drop that hurts energy because the fans have to work harder, the heat transfer is not as good, and to prevent the need to go out on a periodic basis to have the coils cleaned to be able to keep them back in good shape. So this has been around for quite a while, what we call that coil maintenance. But in this day and age, we're really looking at airborne pathogens. The virus is not going to stop on the fin. It's going to fly right through there. So you can see now we've upped the density in terms of the number of lamps in the photograph to the left. And in the center photograph, even more so. Maybe instead of being 40-inch centers, we'll go to 12-inch or maybe even down to 6-inch centers to be able to get that intensity necessary for what's only going to be in that section for less than a half a second. Remember, we have duration to look at as well as intensity. So again, looking at these factors to make sure we pull together the appropriate solution. In a duct, as suggested by the graphic on the right, we may actually turn the lamps to be parallel with the airflow and maybe populate them down that straight run, again, in order to get the strength that's necessary to do the job. This is a chart that I kind of chopped down to only show a few. There's probably 80 or 90 different organisms on the chart I was looking at, just to show you how the UV has a requirement of more or less power, if you will, based upon what you're looking to kill off. Again, mold taking a whole lot more, but on coil maintenance, that mold sits still. So your duration works for you. You have all day to work on it. Whereas a virus is, you don't have that period of time. You need the intensity, but you also need less to get the job done, as suggested here by the requirement here to the right. If you really want to go to a best solution, let's go back to our HEPA filter and look at the UV as well, and then say, hey, let's take advantage of the HEPA, which captures the virus, the bacteria, stops it in its place. So now you're going to be able to boost duration. At the same time, you turn on your UV lamps, and basically you have this capture and kill arrangement where, in fact, you've taken it out of the airstream to a significant extent with the filters, and then you have the time with the UV lamps to deactivate, to kill off the virus at the same time. You might say belts and suspenders, but really where, in fact, you're looking at something that really cannot afford to say, hey, maybe we've got a lamp out, we better make sure that HEPA filter's there, or we don't really like the fact that we have the technician going in with the HEPA filter that may have more or less level of viable virus on it. This might be a solution that you want to keep in mind. Again, some practical considerations looking at the ultraviolet. Once again, downstream of a pre-filter, the lamps will deteriorate in terms of their output if they become soiled with dirt, with any kind of a film. Easy to clean off, but certainly the better the pre-filter, the better the performance there. You may be aware that UV is not particularly friendly to a lot of materials. So paper, synthetics, certain insulations, maybe even some insulation of wiring. You need to make sure that, in fact, it's UV tolerant or shield these items from the direct line of sight from the UV itself. Fiberglass pre-filters, for example, are fine. Paper filters over a period of time will degrade. You won't have to take them out when you replace them. They'll be gone. You just have to put the new ones in. So in all seriousness, you want to take a look at that to make sure the materials are in good shape for the area where the lamps will be installed. UV lamps have a characteristic that when you take them out of the box, plug them in, they'll have that 100% output. And they sort of have a break-in period where that 100% will drop down to 90 or maybe 85% after maybe 100 hours of operation or so. And then it flatlines for about a year, at which time that will then drop off again. And the UV that you need for killing off the pathogen starts to go away, even though the lamp may still look to be glowing. Recognize that the C band is not something you can see with your eyes. It's invisible to the eye. So you do need to replace them manually. You can use an hour meter or perhaps a radiometer, a little more sophisticated in terms of some feedback for changing them out. But this is not an option. This is a requirement if you're looking to go after this virus, that you change them on that periodic basis. You can perhaps extend that life by leaving them energized. Now, if you have a school or an office where you'll be running the HVAC, you know, 12 hours a day, maybe more. I would say leave them on 24/7. If in fact you're only going to use this zone periodically, then maybe you can go ahead and shut them off. It won't be much of an impact. But just in general, unlike the ionizers, I would say it'd be best just to leave them on. Disposal, the lamps have mercury. Old ballasts have some PCBs and so forth you have to be concerned about. The newer ones, not the case, but they do have recyclable materials, so you need to obviously dispose of these components accordingly. And just as the UV wasn't very friendly to the synthetics and the paper, they're not very friendly to your skin or your eyes. Do install door interlocks on a retrofit. Obviously, for new equipment, you would have them coming out of the factory, and a warning label would be a good idea as well. Now, the last of the four technologies, if you will, I'm going to look at is something that is sort of derivative of UV, if you will. Not that well known, relatively new in the use for HVAC, but it's been a very effective solution for some advantage in going after several different types of airborne contaminants. The airport industry seems to have embraced this as much as any vertical market at this point, and that's because they have so many different types of contaminants of concern, whether it be the outdoor jet fuel, or whether it be people, or whether it be the food court, the restrooms, that they're looking for something that has a low pressure drop and effectiveness for trying to treat all of these particular concerns. Now, of course, they're concerned about COVID-19. So what we're using here is the same UV lights to irradiate, to energize a catalyst that is on a flat 1-inch thick panel. Blowing it up, you can see it's a hexagonal cell that has a catalyst coated to the surface, so lots of surface area. And the activity with regard to converting odors and VOCs, as well as deactivating pathogens, occurs right at that surface, not unlike what you see with bipolar ionization, with hydroxyl radicals coming into play and so forth. Just another graphic here where we have the lamps to the left, airflow going from left to right, going through the panel in the middle. In this particular example, we're showing formaldehyde, but it could be any contaminant you're looking at here, including the pathogen. Comes out the other side all cleaned up. Once again, this is not 100% single pass. You're probably, very much like bipolar ionization, 10, 15%, 20% perhaps on a single pass. But over time, as the air recirculates, does a very nice job with regards to removing these particular contaminants. Now, we're talking about VOCs and odors. That's all well and fine. It does, however, have a very strong effect with regards to germs. Much of this is UVC lamps by themselves. I'm getting some different information, as a matter of fact, with regards to how much the catalyst actually contributes to the germs. But in any case, for an application we know that they're going to be chasing the COVID-19, we would bump up the density of the UV to make sure you get your best performance. Photograph of a system itself. This is a section of an air handler in a factory. The gray panels, lower left, upper right, are the catalytic panels themselves. The other two have been removed, and you can look through and see the UV lamps behind them that are not energized at this point in time. They're about 6 inches off the panel. The overall depth of this assembly is only about 12 or 14 inches, so it doesn't take up much space. And one of the advantages is it's very, very low pressure drop. These panels probably only 0.05, maybe 0.1 inches of static pressure loss. They are not consumable. You can take these out and wash them out should they get dirty over time, just as you might eventually have to clean a cooling coil. So it's very simple. It's basic with regard to what it does. It's easy to maintain, and something that you may want to look at for some application where, in fact, you're looking at the virus, but may have to chase some odors and other concerns as well. Okay, I'm going to come here pretty close to a wrap with regards to this presentation. Hopefully I've given you some good information about these individual technologies. Just a quick summary here. Going back to filtration, I certainly would encourage you, if you have a lower efficiency filter, to try to get that upgraded to at least a MERV 13. And obviously, the more the concern, the more the capability of the system, moving more and more toward, again, that gold standard using the HEPA filter itself. Obviously, there's pressure drop and space constraints that you have to look at, the energy associated with that, and the maintenance for the filters that come into play. I would say it's certainly a better solution for capture, and maybe more than better. We can set these up with the HEPAs to be almost a best with regards to performance going after the coronavirus. Bipolar ionization, we're talking about a less costly and maybe more flexible solution, but again, with lower cost, you're going to see lower efficacy as compared to some of the other options. I would call it a good with regards to deactivation and kill solution. Nice in that it's, as your air is continuing to recirculate, it is continuing to attack some of these guys and mitigate the concern that we're trying to deal with. Ultraviolet, again, there's some system considerations we have to look at when we pull it together for you. Again, you need some space. You need to have the ability to get into to service it. There is a replacement of the lamps that comes into play, but we can size this and provide the components to give you extremely high efficacy, not unlike what we can do with a particulate filter leaning toward the HEPA, a better or almost best solution as well. And at that one slide I showed you with a capture kill, this would be clearly a best where you're taking the strengths of the capture approach and the deactivation approach and combining them with respect to a solution that's going to be very powerful. We can't say 100% for any of these. There's too many, Murphy lurks around every corner and to create problems there. But certainly that last one, if you don't get 100%, you're going to get awfully close to it, providing things are installed and maintained properly. So here's, again, technologies, approaches, hopefully some information with regards to the practical considerations for all of them. And at this point, I think maybe I turn it back to you, Andy, here with regards to how you move forward on providing these solutions.
Yeah, and we'll have some extra time here for the next few minutes to do some question and answers. There's been a couple of questions that have popped up during your presentation, so we can try to address those now. One of the questions is, will humid environments affect efficiency of either of these technologies?
Will a human environment?
Humid, yeah.
Oh, humid, I'm sorry. As a matter of fact, humidity does come into play. If you have an absence of humidity, for example, with PCO, where you really need to be able to create these hydroxyl radicals, you don't have the building block from the water molecule, so a very dry environment, it may not be as effective as something that's more humid. Bipolar ionization, the same way to some extent. Extremely high humidities, you could see a situation where there could be maybe an acceleration of the reassociation of the ions, that hydrogen ion and nitrogen ion that would perhaps reduce somewhat the effectiveness with bipolar ionization, but that we had not found that to be significant. So it does have a play. I think my biggest concern would be if you had a Phoenix, Arizona site that was very, very dry, that PCO may not be the product that we would be suggesting.
Okay.
Incidentally, if I can just add on to that, the lamps themselves can go up to basically 100%. They're really immune with regards to the humidity for ultraviolet.
Okay. We've got another one that says, what would be the most cost-effective approach to integrating this into a packaged rooftop DOAS unit?
Well, okay, you said DOAS, so now I have to stop for a second. Theoretically, the outside air unit is treating clean air. So are you at the exhaust fan from the hospital infectious disease, ward that's dumping the coronavirus into your outside air machine? Or in fact, you're actually treating true outdoor air that theoretically should be rather clean? If that's the case, you may want to save a couple dollars and put your budget toward treating the air that's being recirculated within the zone as opposed to the outside air itself. However, if you're looking at a package system, rooftop unit of one sort or another, you're now going to look at limitations associated again with what space is available, what fan power is available. Obviously, we're always looking at budget, but that is somewhat limiting in terms of the available space. You can't put a 12-inch HEPA into a rooftop unit. Obviously, the space is not there. You could put it downstream in the ductwork perhaps, but are you going to have the static capability to overcome the new pressure drop that you've introduced? So in that case, you might say, it looks to me like bipolar ionization will be a good solution, or maybe you could put UV, if space allows, immediately after the coil in the rooftop unit, in the smaller, less space-friendly system, and with a high output lamps, and have some very good performance, providing again that you're going to have enough space behind that coil and before the fan to be able to install the lamps themselves. Probably best to look at the individual unit that's being considered to see what they might the best approach might be.
Okay. Chuck Hammock has asked us to speak about far UV used in occupied spaces. I know there's some electrical lighting companies. GE, I think, is one of them that has a different UV band that can be used. I'm not going to claim to be an expert on that. We've got some people that know lighting reps. If you've got questions, we can kind of direct you to that. Unless, Dan, you've got some information that you want to share on that.
One note I might say is that we're talking today about things that are going to be installed in ductwork or in air handlers or fan coil units and the like. There are products out there that are room UV devices which sit up at the ceiling, which I think have different types of models. Some that you only turn on when the room's been, the people have left, when it's unoccupied. Others that I think can stay on all day long. And as the air just normally circulates around and the pathogens come inside that device where the UV lamps are located, they get to do their work. I'm not sure that's what we're talking about here. It's my understanding, however, that UV, the C band, is the one that's most effective with regards to going after the pathogen, whether it be a room device or whether it be something that's in your HVAC system.
Yeah, Chuck, I would just say reach out to, have one of your electrical engineers reach out to one of their lighting reps. I'm sure that UV in spaces is probably handled more by that group. So I guess one of the other questions coming across is if we can discuss statistical data, effectiveness of bipolar product. We mentioned ASHRAE data of 99% more effective. Do we have any data on our 10 to 20% effectiveness for bipolar ionization? I know that we've talked, and it's very hard to replicate real world situations in the lab. But, can you speak to that at all?
This is a real challenge for the suppliers of these types of products. People say, well, how well is it going to work with COVID-19? And facetiously, I say, well, we've contacted the CDC and asked it for a vial of that virus so we can do some testing. And before the vial was delivered, I had a policeman knocking my door thinking I was some kind of a bioterrorist. The reality is that we cannot get our hands on these types of samples, and not that BioClimatic as a company would anyway, but even laboratories are very, very cautious when you're talking about testing devices for that have infectious diseases involved. We work with a laboratory that's actually not too far away from where our facility is located that uses a surrogate for tuberculosis. They don't even want to touch tuberculosis, and they're a full-blown certified laboratory. So as you can imagine, when we're looking at something like ionization with respect to its efficacy for COVID-19, much of this is based upon experience and the understanding of the process, not on test data that we could say it actually would be 24% under these sets of conditions. We do know, as you saw on the slide showing the chamber tests, that it's extremely capable of getting the job done, and we know exactly how that works. But how it comes into play in a real-world HVAC system is a different matter altogether. And much of this is our best estimates. We'll obviously, hopefully over time, be able to gain more information about this with what we learn. But right now, it is really best estimate based upon the understanding of the technology, what happens within the chamber tests, and our experience with regards to how the effectiveness occurs with other types of contaminants of concerns, odors, and the like.
Okay. The next one's popped up is, can bipolar ionization be combined with UV filtration?
Yes, it certainly can. I'd be inclined to say if your budget allows going with the UV, maybe that would be sufficient. That having the two of them combined may not provide an additional benefit, since we can get the UV to probably run 85, 90%, 90% plus in terms of its effectiveness against the virus for most systems. Now, again, high-speed duct systems, that may drop off a little bit. But in any case, it's going to do a very, very good job. So the added value of having ionization, I'm not sure whether I see that makes sense. There's no reason why you couldn't. They're not going to contradict or pose a problem for one another. But I would say if you have the space and you have the budget for UV, that's probably the way that I would go instead. Now, the advantage of the ionizers is they take up a lot less space. They're very simple devices. They're not consumable. You may have to clean them periodically, but if a budget is a concern, but you really want to do something to try to mitigate what's going through the air, then tilt in that direction with regards to good, better, best, not only performance, but also for budget.
Okay. I think your answers previously have touched on this one, but can you speak to why ASHRAE is not backed any technology other than UV in killing pathogens?
That's an interesting topic. ASHRAE they have not said no, but they have not said yes. And largely it's because of the same question that I just answered a minute ago. It's been very difficult for many of the suppliers to pull together data on what's happening in HVAC systems as opposed to chambers. The ASHRAE folks have seen chamber tests, they understand that, but they say we really like to see what happens when you've got something coming in the return air and then something being discharged out the supply air register into a zone in terms of performance. So they've been quite focused in terms of that, and over time more and more data has been presented. To be perfectly frank, there's an element within ASHRAE that has had a political edge to it. We don't want to go down that path here today, certainly. But there has been a concern there with respect to isolating a couple of technologies. Ionizers is one of them, where they seem to be particularly focused on gaining more third-party testing. But again, with regards to COVID, that data just simply does not exist.
Okay. Another question that came into me privately, which I think you can speak to, is any concerns with the use of bipolar ionization with respect to safe ozone levels?
Wonderful question. Although they say if you're giving a presentation, you should never say that's a good question. That's not the way you give a presentation. So I'll say that's an interesting question. We do provide, and we have provided for years, a different type of ionizer, a tube type of ionizer, which is very, very capable with regards to getting rid of casino smoke and other air quality problems. But yes, it does produce some ozone. Maybe only 30% of what ASHRAE says is what you want to see in a space, but nonetheless, it does produce some ozone. Over time, technologies have changed. We now have the needlepoint style, and that produces what I'll call zero ozone. Let me qualify that. Where in fact, the tube certainly produces something that can be measured. The needlepoint is down at 0.0005 parts per million. It's extremely small. And in fact, our ionizers, our needlepoint ionizers have been tested to be in accordance with what's relatively new, the UL 2998, which is a quote unquote zero ozone device once certified. But within the small print of that standard, that limit is 0005, just it turned out to be coincidentally. And the reason is that you don't have instrumentation that can reasonably check much below that. And there's too much can come into play that could be creating ozone, whether it be a copy machine or somebody scuffing their feet in the carpet that may interfere with those readings. So for all intents and purposes, a needlepoint is a zero ozone device. It has no impact with regards to what is seen as a clear pollutant in and of itself, no doubt about that. And we, as a company, do not tend to gravitate toward the old tube for any space that is considered an occupied zone using bipolar ionization. We recognize that, and we certainly endorse that.
Okay. And then the last question that I'm seeing, would you lose your static charge on your MERV 13 filter because of high humidity and particles insulating the charged fibers and chemicals in the air from bus, truck, and jet fuel?
Okay, I'm not sure if I'm hitting the question nail on the head or not, but there are filters that can be bought that are have a static charge coming out of the box. And I'll liken that to when you were a kid and you took a balloon and you rubbed it on your wool sweater and you stuck it on the wall and you got your giggles because of the balloon would stand there and not fall off the wall. Except after a while that balloon did fall. Give it 3 or 4 minutes and it was now lying on the floor. Well, that's very much like these passively charged filters that you get out of the box. They will lose their static charge over time naturally, and therefore the effectiveness that's based upon the charge goes away. Now, that's not like powered filters, which have an electrical source that maintains a static charge permanently. That's a different category. But if you're buying a filter for, it's a MERV rating that is a statically charged out of the box, charged filter, I would consider perhaps looking in a different direction. Just go to the next level up. Instead of a MERV 10 that's got a charge, I go to a MERV 13 that does not.
Right. And we do have a product that's an electrostatically charged, permanently charged via electricity, that's got a lower pressure drop and a higher MERV rating. If that's something that people are looking for, ask your account exec if you want to look into that. But that's the last of the questions. Obviously, if you've got any more questions and you want to talk about applications, just reach out to your local account executive. Dan on the last slide's got some pictures of custom air handlers that BioClimatic's built with higher levels of filtration in them. So, we can build an entire system if you need it. So additionally, this does qualify for PDH credits for Georgia, North and South Carolina, and Florida. Please email your account executive and let them know that you attended the webinar and that you'd like your PDH credit, and we'll get that emailed out to you. We also recorded this, and it will be available on our website later on today. Tony is nice enough to go ahead and send that link in the chat. Additionally, there's a link for the resources that we have where all of our past webinars are on there, and you can go online and watch them, share them with other people in your organization or students if you want. I appreciate everybody's time today. Tony's going to be doing another webinar later on. Tony, do you want to speak to that?
Sure. Thanks, Andy. And thanks, Dan. That was a great job. And appreciate everybody joining us. We're Thursday. I just put out a link in the chat for the next webinar. It's makeup air units and restaurant applications. So come and join us Thursday. Can't remember exactly the time. I think it's a 10 to 11 or 9:30 to 10:30, something like that. When you register, you'll get to see the time. So thanks, Andy. I appreciate it.
Yeah, I appreciate everybody's time, and reach out to your account execs to get your PDHs, and give us a call if you've got any other questions. Thanks for spending your lunch hour with us.
Thanks, Andy. Thanks, Dan.
Thank you.
Dan, I'll call you later today, okay?
That
You did
sounds
great.
I'm going into another webinar right now, and I've got some emails that are backed up, but I do want to spend a couple minutes with you. So yeah, give me a shout.
All right. Thanks a lot.
Yep. Thanks.
That was good. Chris, you still there?
I'm still here, yes.
I think Andy's gone.
I'm trying to leave. I'm just trying to look where I can shut the thing off.
I'll kick you off in a minute, no problem.
When
Hey, thanks,
Chris
guys.
shuts down, it'll all shut down.
Hey, thanks much.
No, you did great, Dan. Thank you.